Hey guys, in this video I will build the state-of-the-art denoising diffusion models from physics first principles. By the end, we will have trained an actual image generator in PyTorch. The plan is simple. We start with a drop of ink in a pitcher of water, then we put a charged particle in that same pitcher, write down its equation of motion, find how its probability evolves in time, and define something called the score. Then I will show you that an image is nothing but the position of that particle in a very high dimensional space, and every single equation we derived carries over without a single change. So let's start with the ink. Imagine we have filled the pitcher with water. Now we release a drop of ink in it. At first, the ink is concentrated at one location, but then it spreads out, or in other words, it diffuses through the water. The reason for this spreading is the kicks by the molecules of water. And if you ask how fast the ink spreads out, that is set by a constant called the diffusivity, which we call D. The diffusivity is mainly due to those kicks, and it's set by the density of the molecules, the temperature, and other features of the water. Now let's pour out the water mixed with the ink, refill the pitcher with pure water, and this time place a bunch of electric charges around the pitcher so that they make an electric potential energy of the following form. Here, X is a position inside the container, so it is a vector with three components. And sigma is just a matrix with constant components that presents how we arrange the electric charges in the pitcher. We will assume it is diagonal with 0.3 along each direction. Now we place a tiny particle with an electric charge of +1 inside the pitcher and wait a little while for it to settle. The potential energy of the particle is simply its charge, which is 1, multiplied by the electric potential. In the following cell, let's first plot this potential energy so we have a sense of its magnitude in terms of the position of the particle. We use colors to represent the value of the energy, and we use the x, y, and z axis for the physical coordinates inside the pitcher, assuming the center of the coordinate system is at the center of the pitcher. As you can see, the energy is 0 at the center and increases as we move away from the center. Let's now get back to how our particle moves around in the pitcher. Here's what happens after we release it. Just like the ink, the water molecules start to kick the particle around, trying to diffuse it throughout the pitcher. However, this time we have an opposing force. In physics, a particle tends to move toward the minimum of its potential energy, which is where the blue color is in the figure above. So the thermal kicks from the water molecules add random motion while the potential energy pulls the particle toward the center. Therefore, the particle jiggles up and down and roams around the center forever. Now let's derive an explicit solution for how the particle's position changes with time after we release it. As we discussed, there are two forces acting on the particle. One is deterministic due to the potential energy, and the other one is stochastic due to the thermal kicks of the water molecules. First, the deterministic force. In physics, the force is the negative gradient of the potential energy. And for our quadratic potential, that is just minus sigma inverse times x. Now, because the particle is submerged in water, it does not accelerate. It experiences viscous drag and reaches a terminal velocity proportional to the applied force. The constant of proportionality is called the mobility, and it measures how easily the particle slips through the water. If you set the temperature to 1, the mobility becomes equal to the same diffusivity constant d we discussed above. So the deterministic drift velocity is minus d times the gradient of u. Now the stochastic force. The random thermal kicks constantly move the particle in unpredictable directions, and the intensity of that spreading is again governed by the diffusivity d. To describe the zigzag path that the particle takes over time, we combine both the deterministic drift and the random kicks into one equation, which in physics is called the Overdamped Langevin equation. Using the conventional stochastic calculus notion, The change in the particle's position dx over an infinitesimally small time step dt is given by the following. Here, dw represents the zigzag random motion, which in physics is called Brownian motion. It mathematically captures the random, uncorrelated nature of the kicks that the water molecules apply to the particle. Let's now solve this equation. For our particular potential with sigma equal to sigma squared times the identity, the gradient of u is just x over sigma squared. So we bring that term to the left-hand side and write the equation like this, where we have defined the constant lambda as d over sigma squared. Now we multiply both sides by e to the lambda t, and we recognize the left-hand side as a total differential. Then we integrate both sides from 0 to t, and we get the solution. Here by x, we mean x at time t, and by x0, we mean x at time 0. Let's now get into the Brownian motion piece. Since the increments at different times are independent, we model dw as a number drawn from a Gaussian with a mean of 0 and a variance proportional to the time step, which is what this delta function is expressing. Now, to make our life easier, let's define j to be the entire second term of the solution, so that x is simply x0 times e to the minus lambda t plus j. Let's find the mean of j first. Since the expectation of dw is 0, the mean of j is 0. All we need at this point is the variance of j. After we use the delta function, one of the two time integrals is removed, and the variance comes out to be sigma squared times 1 minus e to the minus 2 lambda t. Let's from now on refer to this variance as v of t. Now that we have the mean and variance of j, we can write the solution in this compact form, where epsilon is a random number drawn from a Gaussian with mean 0 and variance 1, so that the whole term has variance v of t. That means whenever we want to predict the value of x at a specific time, we just randomly pick a number from a normal distribution and use it as an epsilon. And this is very easy to implement in Python. So in the following cell, we implement exactly that. We solve the Langevin equation step by step and release the particle at the corner of the picture far from the center, so that we can clearly see it move in a zigzag way toward the center where the potential energy is minimal. That zigzag is the Brownian motion we just worked out. Note that the particle never settles exactly at the center. It moves around it forever because the thermal kicks never stop. But because of the pull of the potential energy, it never goes far away from the center either. The uncertainty in the particle's position around that minimum at this later stage is set by the diffusivity d of the water. Also note that at this stage, although the particle itself is not static, its probability is. The probability of finding the particle around the center is no longer evolving with time. So we can say the system has reached an equilibrium state. And if you ask what this late stage probability is, thermodynamics gives you the following equation. It is the exponential of minus the energy divided by z, where z is just a normalizing constant that makes sure all the possibilities add up to 1. If we substitute our explicit form of the potential energy into that integral and carry it out, we get a number that is roughly 2.588. We could actually compute this value because we are living in only 3 dimensions here. But later, when we go to higher dimensions, we will no longer be able to compute z. So for now, please keep in mind that z is just a constant that we want to get rid of. And getting rid of it is the whole advantage of the score matching method that we will see below. Let's now plot this probability to see where we are most likely to find the particle. To clearly see where it has its largest value, we show it on a logarithmic scale. As you can see, the largest probability is at the center of the picture, exactly where the energy is minimal. Also note that the width of this probability distribution is not 0, and that is why the particle's position was still zigzagging around the center. If that width was 0, meaning the probability was a sharp spike at the center and exactly 0 everywhere else, then the particle would have no probability of being anywhere except at the center, and we would see a particle with no zigzag at all. Now you might ask, what about the probability right at the moment we release the particle? It obviously evolved with time. Is there a way to quantify that time evolution? The answer is yes. Physicists have done that already. There is an equation called the Fokker-Planck equation that tells us how the particle's probability evolves in time. Here, P of x and t is the probability of the position of the particle at time t. D is the diffusivity, the upside down triangle is the gradient, and the upside down triangle squared is the Laplacian. Let's first check whether the end stage static probability that thermodynamics gave us, the one we just plotted, is actually a solution to this equation. For that, we simply insert that probability into the equation. We already know the time derivative on the left is 0, so let's look at the two terms on the right. Since p is the exponential of minus u divided by z, taking its gradient gives us minus the gradient of u times p. So wherever the combination of gradient of u times p shows up, we can replace it with minus the gradient of p, and u drops out entirely. Doing that substitution in the first term on the right-hand side turns it into exactly the negative of the second term. So the two terms cancel and the equation holds. This confirms that the static thermodynamic probability is indeed the equilibrium solution of the Fokker-Planck equation. Now comes another question. This is obviously not the only solution because we watched our particles' probability evolve with time, and this one does not evolve at all. So the specific question is, what sets the solution that we actually observe? The answer is the initial condition, which is the probability distribution of the particle at the moment we released it. And I want to emphasize the notion here. Since x0 is the initial position of the particle and we set it ourselves with certainty, the probability of x is conditioned on x0. So this is a conditional probability. But that conditional probability still satisfies the Fokker-Planck equation because its difference with respect to the unconditional one is just a normalizing constant, which cancels out in the equation. Since we place the particle at a definite starting point, this initial probability is delta function centered right there, meaning we are completely certain about its position at time 0. The Fokker-Planck equation then evolves that sharply peaked spike forward in time, gradually spreading it out and drifting it toward the center, until at very large times it settles into the equilibrium solution we found above. So what does the solution look like in between, at the finite times where the probability is neither the initial delta function nor the final equilibrium? Because our potential is quadratic, the drift is linear in x. And this is exactly the setup of what physicists call an Ornstein-Uhlenbeck process. This is one of the very few cases where the Fokker-Planck equation can be solved exactly in closed form for any initial condition. Starting from our delta function, the exact time-dependent solution is a Gaussian whose mean shrinks toward the center and whose variance grows towards sigma squared. And notice that those are exactly the same lambda and the same v of t that we already defined when we solved the equation of motion. Notice that at time 0, v is 0 and the mean is exactly x0. So the solution collapses back to the delta function we started with. And as time goes to infinity, the exponential goes to 0 and v goes to sigma squared. So the solution turns into the centered Gaussian, which is the same equilibrium solution we found before. In between, this formula tells us exactly how that sharp spike of certainty spreads out and drifts toward the center, one Gaussian at a time, which is precisely the zigzag toward the center behavior we saw in the animation. But wait, isn't this solution just a normal distribution? Yes, it is. So we can write it compactly like this, where the mean is x0 times e to the minus lambda t, which is exactly where the particle would end up if there was no thermal noise at all. decaying exponentially from the release point toward the center at a rate lambda. And the covariance matrix is V of t times the identity, which means the covariance is isotropic, the same variance along each of the three axes, with no correlation between them. That variance is entirely due to the thermal kicks, and it tells us how uncertain or how spread out our knowledge of the particle's position is at time t. Now let's define what is known as the score in the generative modeling literature. It is simply the gradient of the log of the probability, which is also the gradient of p divided by p. Let's substitute our time-dependent solution into this definition. If we write out the Gaussian explicitly, the log has two terms. The second term does not depend on x at all. It is purely a function of time. So the moment we take the gradient with respect to x, that term vanishes, and the score reduces to minus x minus the mean, divided by v of t. And let me emphasize something important here. By taking that derivative, we eliminated the normalizing constant of the probability distribution, the one we called z. If we ask why this matter, here is the short answer. In our picture, x lives in 3 dimensions. So we could actually sit down and compute z by hand and get 2.58. But once we move to realistic generative modeling problems where x might represent all the pixels of an image, we are working in spaces of thousands or millions of dimensions, and the integral defining z becomes essentially impossible to compute. So having an equation that never requires us to know z is a huge practical advantage. And that brings us to the second half of this video, which is the generative AI part. Let's start with the vector x. In our example above, we release the particle at the position 3, 3, 3. Let's just repurpose that vector. Let's say I have an image with 3 pixels whose values are all the same, 3, 3, 3. In the following cell, we plot that image. And as expected, it is a uniform image, since all the pixel values are the same. But we could have released the particle anywhere we like. That means the pixel values of this image could be anything we like, for example, 0, 3, 1. But wait, what about a real picture? Let's say an image of a cat. In the following cell, we import a cat photo, convert it to grayscale, and plot it. And in the next cell, we print out its pixel values. So the pixel values are just a bunch of real numbers, exactly like the position of the particle. The only difference is that our particle's position was a vector with 3 components, while this cat image is an array of shape 300 by 451. But that is just a convention. We can change the convention and represent the cat image by a vector made of those same numbers. We simply take the second row and place it right after the first row. Then take the third row and add it to the end of that. And continue until we have just one long row, which is now a vector with 300 times 451, or 135,300 components. And that is the dimension of our image space. So in the following cell, we flatten the cat image and call it x0, corresponding to the position of our particle at time 0. Now you might ask, the Langevin equation and the Fokker-Planck equation both lived in 3 dimensions. Well, not really. They both had vector forms, and those forms are defined independently of the dimension. Let's just see what we mean by gradient, divergence, and Laplacian in this high-dimensional image space. The gradient of a scalar function is the vector made of its partial derivatives with respect to each component of x. The divergence takes a vector field with one component for each direction of x and adds up how each component changes along its own direction. And the Laplacian is just the sum of the second derivatives with respect to every component. With these definitions in hand, the Langevin equation for our cat image looks exactly the same as before, just with x living in 135,300 dimensions instead of 3. And likewise, the Fokker-Planck equation governing the evolution of the probability, which is now the probability of the image at time t, is completely unchanged. So the form of the equation is exactly as physics prescribed. The only difference is that x, the gradient, the divergence, and the Laplacian are now computed using all those high-dimensional components instead of just three. And it is important to note that x is not restricted to particle positions or images either. For example, in AlphaFold 3, released by Google DeepMind, the positions of the atoms of a protein at time zero are represented by a high-dimensional x0, whose components are the x, y, and z coordinates of every atom in the protein, one triplet per atom, all concatenated into a single long vector. At this point, the natural question is, if x0 represents the cat image, then what does x represent? The answer is the diffused cat image. To see what I mean, let's assume we still have a variance of 0.3 and a diffusivity of 0.03, the same values we used for the particle. Now let's use the Langevin equation to see what happens to the image at later times. In other words, if x0 is the pixel values at time 0, how do the pixel values evolve in time under the Langevin equation? In the following cell, we solve the Langevin equation and make an animation of the values of x at every time step. And as you can see, everything is exactly like the case of the particle. At time 0, the image shows the cat, and that corresponds to the initial position of the particle in the picture. As time passes, the pixel values start a zigzag motion toward the minimum of the energy, which we assumed to have exactly the same form as for the particle, with the only difference being that it now lives in a much higher dimension. After a while, the pixel values arrive at the equilibrium state, after which they just continue their zigzag motion around that point, again just like the particle in the picture. That means the probability of the image has evolved in exactly the same form as for the particle, which we can then use to find the score function in exactly the same way, with the same mean, the same variance, and the same lambda as before. Now you might say, I'm not interested in diffusing the cat image. I want to generate it. Well, that is not a problem. Just replay the animation in reverse, which is what we do in the following step. But here is what running the animation in reverse means mathematically. It turns out that simply flipping the sign of the time interval dt in the forward Langevin equation does not give you the correct reverse process. Running a diffusion backward in time also requires correcting for the fact that probability has been flowing from the sharp initial spike toward the spread out equilibrium, and that probability flow has to be undone. And that correction is given by the score we defined above. The result is known as the reverse time stochastic differential equation, or STE, or the Anderson STE. It adds a score-dependent correction term to the drift and runs the same equation backward. Here, tau is a reverse clock that increases as the actual time t decreases from t, which is noise back to zero, which is the cat image. And the dw is Brownian motion with respect to that reverse clock. Notice two things. The drift term flipped sign relative to the forward equation, and it picked up an extra correction term of 2d times the score. And that is precisely what pulls the noisy image back toward the data, undoing the diffusion. Let's now implement this reverse mode equation in the following cell. We start from a randomly selected noise image, but we use the same score and that same potential as before, and we see what the end image looks like. And as you can see from the animation, the noise evolves over time and becomes the cat image. So let's recap. To create a cat image, I can assume a probability of this Gaussian form, assume this form for the mean, this form for the variance, define lambda as d over sigma squared, set sigma squared to 0.3, d to 0.03, and that is it. But there is a problem. If we set all of these, we get back to the exact same cat image. So how can we get a different cat image? If we look at the mean of the probability, you can see that it depends on x0. So one way to get a different cat image would be to change the components of x0 and set them equal to the pixel values of a different cat image. But that would be useless. I don't want to generate the images I already have. I want a new cat image that I don't have. For this reason, we use conventional probability to introduce the marginal probability. It is the integral of the conditional probability times the probability of x0. And the integral runs over all possible nice-looking cat images, whether they already exist or are new ones we might generate in the future. Intuitively, this is the probability of x at time t, regardless of which nice-looking image we started with. And this is how we take into account the new images that have not been generated yet. In this equation, we assume that all the nice-looking images, both the ones we have seen and the ones that have never been generated, have some probability distribution p of x0, which is unknown to us. But don't worry, we will handle that later. Now we can repeat everything we did above, with the difference that this time we use the marginal probability instead of the conditional one. And we keep in mind that since the difference between the two is just in their normalizing constants and not in the form of their energies, both of them satisfy the Fokker-Planck equation. So now let's define the marginal score function. The equation is the same as before, except that we now use the marginal probability. And let's do a straightforward calculation to write it in terms of the conditional score function, whose form we already know. We write the marginal score as the gradient of p over p, then substitute the integral definition of the marginal probability, pull the gradient inside the integral, multiply and divide by the conditional probability, and we end up with the conditional score sitting inside the integral, weighted by this ratio. To generate a new cat image, we get back to the reverse time STE and replace the conditional score function by this marginal score function. Everything else stays the same. But how do we estimate this marginal score function? Our objective is to learn the marginal score, because with that we can solve the reverse time STE and generate images we have never seen before. So we define a neural network S of theta that estimates the marginal score. To train it, we want to minimize its difference with the real marginal score. More specifically, we want to minimize the following expectation value, where t is a relatively large time period. But now we have a problem. We don't know p of x0, and therefore we don't know the marginal probability either. And now comes the surprise. Through a straightforward calculation, one can show the following. The loss written with the marginal score is equal to the loss written with the conditional score, plus a constant. This means inside the expectation value, we can replace the marginal score with the conditional score, and the difference is just a constant that does not depend on the parameters theta of the network. As a result, we can equivalently minimize this new objective, which is written entirely in terms of the conditional score, whose analytic form we already know. But we still have a problem. We fixed the argument, but the expectation value itself still contains the unknown marginal probability. To estimate that in practice, during training, we sum over all the images that we have in our dataset, and then for each image x0, we draw a random x from the conditional probability. And that is it. Now let's explicitly write the conditional score function by substituting the known form of the conditional probability together with the exact solution of the Langevin equation, where epsilon is a random number sampled from a Gaussian with mean 0 and variance 1. After a straightforward calculation, the score reduces to minus epsilon divided by the square root of v of t. Let's now substitute that into the loss function. And there is still one problem we need to solve. Since the variance v of t appears in the denominator at small noise values, that term blows up and the loss becomes unstable. To fix it, we redefine the neural network. Instead of directly estimating the score function, we want our network, which we now call epsilon of theta, to estimate the noise function, which is minus the square root of v of t times the score. And if you plug in the score we just found, that quantity is simply epsilon itself. So our new objective is to minimize this equivalent loss function, which is just a squared difference between the network's output and epsilon. Note what the network is now learning. It is learning to predict the noise that we added to the image by passing it through the Langevin equation. And for that reason, this learning method is called denoising score matching. Now we are ready to actually define a neural network and train it. We set sigma to 1 and lambda to 10 so that at time equal to 1, the exponential is essentially 0. And the domain of time in the expectation value is simply from 0 to 1. And since I want to run this code on my laptop and I don't have much compute power, instead of cat images, I choose to work with MNIST handwritten digit images. Then we loop over mini batches of images, and in each loop, we do the following. We randomly pick an image from the dataset. We randomly pick a time from the uniform distribution between 0 and 1. We randomly pick a noise value epsilon from a normal distribution with mean 0 and unit variance. We use the solution of the Langevin equation to find the noised version of the image. We compute the argument of the loss, and then we use gradient descent to update the data parameters of the network. Let's now implement all of this in PyTorch. First, we load the data. We use the MNIST dataset of handwritten digits. It contains 60,000 training images, each a single channel 28 by 28 grayscale digit. Torch Vision downloads it automatically for us. We resize the images to 32 by 32 so that the image size is a clean power of 2 for the 3 downsampling steps of the unit. And if you don't know what a unit is, here's a simple explanation. Simply speaking, its purpose is feature selection at a scale. We want to pick up the important features of the image and throw out the unimportant information. More specifically, a unit is a U-shaped convolutional neural network originally designed for image segmentation. An encoder downsamples the image to capture context, and a decoder upsamples it back to full resolution. It trains well on small datasets, and its design is now also the backbone of diffusion models. So in the next cell, we define our network, epsilon of theta. It is a small unit that downsamples the 32 by 32 grayscale digit, process it at a coarse resolution, and then upsample it back to 32 by 32 so that the output has exactly the same shape as the input image X. The time t is turned into a sinusoidal embedding and injected into every residual block so that the same network can predict the noise at any diffusion time. And since MNIST digits are single channel and visually much simpler than cat photos, we shrink the base channel widths from 64 to 34, which is enough capacity and train faster. Then in the following cell, we train it using denoising score matching. For each mini batch of digit images with the raw random t and the random epsilon, we form the noised image using the solution of the Langevin equation, and we take a gradient step on the square difference between the network's prediction and epsilon. As you can see, the loss started at a large number and dropped by 1 order of magnitude after 15 epochs. And finally, we generate images. The official name for the numerical implementation of the reverse time STE is the Euler-Maruyama scheme. So in this block, we load the trained denoiser, start from pure noise, and integrate the reverse time STE step by step, where at each step the score is just minus the network's predicted noise divided by the square root of V of t. And here are a bunch of randomly generated new digit images that did not exist before. With this, I conclude this video on denoising diffusion models. And here is a question for you. In this video, we chose a quadratic potential energy for the particle, which gives us a Gaussian equilibrium. What do you think would happen to the training and to the generated images if we picked a different potential? Write your answer in the comments below. And please send this video to someone who might find it useful. Your word of mouth is the best way to support me in creating more videos like this. And finally, I can help you apply these models in your projects. If interested, use the link in the description below to book a short call.